Hello, sir. This is Santana Srinivasan, 20bce1876. I'm from the BTech Computer Science and Technology Scope Department, and today I'll be giving a small presentation on the IEEE standards. Just a minute, let me present the PPT. Yes, so to begin with, why do we need standards? So the need for standards is to make or break the networking products. And the second need for standards is that interoperability, which means the ability of computer systems to exchange and make use of information. And the third need is that they should have a common ground where the manufacturers obey the standardization. So let me give a small introduction on the IEEE standards. Okay, so basically IEEE means Institute of Electrical and Electronics Engineering. So IEEE is one of the leading standards making organizations in the world as it performs its standard making and maintaining functions through the IEEE Standards Association. IEEE standards affect a wide range of industries including power, energy, biomedical, healthcare, IT, telecommunications, transportations, nanotechnology, information assurance, and many more. So in 2005, IEEE had close to 900 active standards, with 500 standards under development. One of the more notable IEEE standards is the IEEE 802, the Local Area Networking, Metropolitan Area Networking Group of Standards, which includes the IEEE 802.3, which is the Ethernet standard, and the IEEE 802.11, which is the Wireless Networking Standard, which is Wi-Fi, the wireless network. And the IEEE standard that I have chose for my digital assignment 1 of the network and communication subject is IEEE 802.11a, IEEE 802.11b, and IEEE 802.11g. So to begin with, the IEEE 802.11 has its own architecture and services. So it's basically known as Wi-Fi as it lays down the architecture and specifications of wireless local area networks, VLANs. So Wi-Fi or wireless local area networks uses high frequency radio waves instead of cables for the connection between devices in local area networks. So users connect by using this wireless LAN system. They can move around within the area of network coverage with the help of these wireless local area networks. So in 1990, the IEEE 802 committee formed a new working group called the IEEE 802.11, specifically devoted to wireless local area networks with a charter to develop a MAC control protocol and physical medium specification. So the initial interest in developing this wireless local area network was for the operating in the ISM band, which refers to the industrial, scientific, and medical band use. Since then, the demand for wireless local area networks at different data rates and frequencies has enormously exploded. And the IEEE 802.11 work group has hence issued a large number of lists, which includes many more new standards. So to give a small insight on the list of standards, the IEEE 802.11 standards have IEEE 802.11a, 11b, 11c, 11d, 11e, 11f, 11g, 11h, 11i, 11j, 11k, 11m, 11n, 11p, 11r, 11s, 11,2, and 11u. So these are the substandards that had been introduced due to the enormous exploration and demand for the IEEE 802.11 work group. Okay, so next is about the IEEE 802.11 terminologies. So basically, these are a few terminologies that we will see in the IEEE 802.11 work groups. First is the access point AP. So any entity that has station functionality and provides access to the distribution system via the wireless medium for associated stations is called an access point. And a set of stations that are controlled by a single coordination function is called a basic service set, BSS. And the logical function that determines when a station operating within a basic service system is permitted to transmit and may be able to receive PDUs. A PDU is a protocol data unit. Next is a system to interconnect a set of basic service sets and the local area networks to create ESS. Okay, so ESS is extended service set, which is a set of one or more interconnected basic service sets and LANs that appear as a single basic service set to LCC at any station associated with any one of the basic service sets. And LCC is basically a logic link control, and MPDU. So MPDU is MAC Protocol Data Unit. So this is a unit of data exchanged between two pure MAC entities using the services of the physical layer. And next is the MSDU, which is the MAC Service Data Unit. In this, the information that is delivered as a unit between the MAC users is stored. And lastly, a station is any device that contains IEEE 802.11 MAC and its physical layer. So the first subunit that I have chose is IEEE 802.11a. So this is basically a standard which was first introduced in the IEEE 802.11 series. So it defines a Wi-Fi format for providing wireless connectivity in the 5 gigahertz ISM band to give raw data speeds of up to 54 Mbps. Although this was alphabetically the first standard to be introduced in the 802.11 series, T was released at the same time as the IEEE 802.11b, which was aimed at connectivity using the 2.4 gigahertz ISM band. Using the technology of the time, the IEEE 802.11 standard was more costly and a little more difficult to implement as compared to the other IEEE 802.11 standards, because it operated at 5 gigahertz rather than the standard 2.4 gigahertz, and therefore it was comparatively less used than the other standards. IEEE 802.11a makes use of the frequency band called UNNI, which means Universal Networking Information Infrastructure. So this is basically divided into three parts. The first is the UNNI 1 band, which has 5.15 to 5.25 gigahertz, and it's mainly focusing on the indoor use. And second is the UNNI 2 band, which has 5.25 to 5.35 gigahertz and is mainly used in indoor or outdoor purposes. And third is the UNNI 3 band, which has 5.725 to 5.825 gigahertz and is mainly focused on outdoor purposes. So next is the advantages of IEEE 802.11a over the 802.11 standard. So since this IEEE 802.11a was introduced much later than 802.11 and was formed as taking 802.11 as the base, IEEE 802.11a, it although utilizes more available bandwidth than the 802.11 standard. So each UNNI band provides 4 non-overlapping channels for a total of 12 across the allocated spectrum. IEEE 802.11a provides much higher data rates than 802.11b and the same maximum data rate as 802.11g, which is also another standard introduced under 802.11 standards. And IEEE 802.11a uses a different, relatively uncluttered frequency spectrum of 5 gigahertz. So there is this process that involves in these IEEE standards. So it is called coding and modulation. So it's basically done with IEEE 802 physical level protocol data units. They're coded and modulated. So yeah, let me explain. I'll just briefly explain the process of coding and manipulation with this. So firstly, this figure illustrates the model developed by the 802.11 working group. So the smallest building block of a wireless LAN is called the BSS, which is a basic service set. So this basically consists of some number of stations executing the same MAC protocol and competing for access to the same shared wireless medium. So a basic service set may be isolated, or it may be used for connecting a backbone distribution system, DS. The AP functions as a bridge and a relay point. In a basic service set, the client stations, they actually do not communicate directly with one another, but what they do is the MAC frame is first sent from the originating station to the AP, and then from the AP to the destination station. Similarly, a MAC frame from a station in the basic service set to a remote station is sent from the local station to the AP, and then it is basically relayed back by the AP over the distribution system on its way to the it's basically acting like a cell. It acts like a building block. So the distribution system acts like a switch, a wired network, or a wireless network in this whole process. So next is the physical layer frame structure. So this is basically a structure which we can find in IEEE 802.11 standards. So here, the primary purpose of the physical layer is to transmit medium across the MAC protocol data units as directed by the 802.11 MAC layer. So there are two layers in this. One is the PLCP and one is PDM. PLCP is basically physical layer convergence procedure, and PDM is physical medium dependent. So when the MAC protocol unit is handed down to the physical layer, it is called as PSDU. So it then prepares the PSDU to be transmitted, and then the PLCP basically adds a preamble and a PHY header to the PSDU. And then we have two types of fields here. One is the signal field and the data field. So the signal field consists of 24 bits encoded as a single OFDM symbol. And the preamble and signal fields are transmitted at 6 Mbps using the BPSK. So here is a small table which denotes the RF signal processing. So here are different data rates, and here is the modulation that it uses. So next is the components of a signal field. So a signal field has 5 different components. First, it's the rate. It basically specifies the data rate at which the data field proportion of the frame is transmitted. R, reserved for future use. Length is the number of octets in the MAC PDU. P is an even parity bit for the 17 bits in the rate, R, and length subfields. And tail is basically a component that consists of 6 0 bits appended to the symbol to bring a convolutional encoder to 0 state. Next is the data field, and it consists of a variable number of OFDM symbols transmitted at the data rate specified in the rate subfield. Prior to transmission, all the bits of a data field are basically scrambled. So now when we look at components of data field, there are 4 major components. First is the service. Service consists of 16 bits with the first 7 bits set to zeros to synchronize the descrambler in the receiver. Since the bits in the data field are scrambled, they're supposed to be descrambled. So the service helps in doing that, and the remaining 9 bits, which is all the zeros, are reserved for future use. And next is a MAC PDU. So this helps in handing down from the MAC layer. And next is tail. This is produced by replacing the 6 scrambled bits following the MPDU end with 6 bits of all zeros used to reinitialize the convolutional encoder. Next is pad, the number of bits required to make the data field a multiple of the number of bits in an OFDM symbol. For example, the data bits used in this particular IEEE standard is 48. So multiples of 48 is used. For example, 48, 96, 192, 288, and it goes on like that. So the next standard that I chose is IEEE 802.11. Yes, IEEE 802.11a was the first one to be introduced, but it was not as widely popularized as IEEE 802.11b was. So using the 2.4 gigahertz, the technology was much easier and cheaper to develop than the 802.11a, which used the higher frequency of 5 gigahertz band. This figure basically gives us an overview of the scheme, the CCK scheme, for the 11 Mbps rate. So how 11 Mbps? It's basically the input data is divided as 8 bits at a rate of 1.375 megahertz. So 8 bits into 1.375 megahertz gives us 11 Mbps. So next is the specification of 802.11b. So here are the different parameters and the values that the 802.11b carries. So the physical layer frame structure of IEEE 802.11b is that it defines two physical layer frame formats which differ only in the length of the preamble. Okay. So the long preamble of 144 bits is the same as used in the original 802.11 DSSS scheme and allows interoperability with other legacy systems. Next is the short preamble, which has a length of 72 bits, which provides improved throughput efficiency. The PLCP preamble field enables the receiver to acquire an incoming signal and synchronizes the demodulator. This basically consists of two subfields, a 56-bit sync field for synchronization and a 16-bit start of frame delimiter, the SFD. The preamble is transmitted at 1 Mbps using differential BPSK and Barker code spreading. So after the preamble is the PLCP header. This basically uses to transmit at 2 Mbps using DQPSK, differential quadrature phase shifting keying schemes. Okay. Next is 802.11g. So 802.11g was one of the main Wi-Fi standards to follow on from 802.11a and 802.11b. Yes, so it plays a very pivotal role in establishing Wi-Fi as the major wireless standard. So its features are listed down here in this table. IEEE 802.11g extends 802.11b to data rates above 20 Mbps up to 54 Mbps. Like 802.11b, 802.11g also operates in the same 2.4 gigahertz range, and that's why they are, comparatively very compatible compared to 802.11a. So the IEEE 802.11 standards do not include a specification of speed versus distance objectives. Different vendors will give different values depending upon environment. To provide the maximum capability while maintaining backward compatibility, 4 different physical layers are used, 3 of which are defined as extended rate physicals, ERPs. These coexist during the frame exchange so that the sender can use any one of the 4 provided they are supported at each end of the link. So next is the 802.11g's packet structure. So this is customary for data packets to be split into different elements. So for Wi-Fi systems, the data packets are sent over radio signals, and it can be thought of as consisting 2 main parts. So these are the 2 main parts. So a PPDO is basically a format into which data is converted by the PLCP for transmission. And PLCP is the PHY layer convergence procedure, which is used for transforming each 802.11 frame that a station wishes to send into PLCP. PSDU, Physical Layer Service Data Unit, represents the contents of PPDU, that is the actual data that is to be sent. And the service is a field that is always set to 8 zeros. The 802.11 service reserves its data and format for future use. So the applications of these three standards are listed down here. So yeah, so this was my presentation on the IEEE standards, and I learned a lot of information from this, and it was very useful and informative. Thank you.